All right. Thanks a lot for the introduction and for having me here. So I'd like to talk about this topic about Siegel modular forms and high algebraic cycles. And I know that so maybe like higher algebraic cycles sounds a little bit mysterious. So in this joint work with Kartik Prasanna, we try to sort of draw a connection between Siegel modular forms and these objects that lead to quite explicit statements that I hope will be sort of approachable, even if they sound a little bit abstract. And for some motivation, I just want to start with these broad conjectures that motivate everything. So first of all, there's the Langlands program, which predicts that sort of automorphic representations, or maybe packets of automorphic representations, should correspond to Galois representations or Langlands parameters or A parameters, depending on your preferences. And today, of course, when we think about the basic examples of the Langlands program, let's say weight 2 modular forms, what we have in mind is not a Galois representation, but maybe even the elliptic curve associated to the modular form. So there's this sort of upgrade you can do of the Langlands conjectures where you actually predict that there's not just a Galois representation, but some geometric object, which is called a motive. So maybe there's some motives whose étale realizations or étale cohomology groups give you the Galois representation. Okay, so you can imagine such a thing. And then the motivic action conjectures within this framework. So this is a set of conjectures that was started maybe with this work of Venkatesh and also collaborators. So there was a similar time a paper of Venkatesh, Harris Venkatesh, and Prasanna Venkatesh, exploring in various settings the following thing. So this is so on the automorphic side, there's this phenomenon that some automorphic representation, so an automorphic rep appears, let's say, in a cohomology in multiple degrees of cohomology. So of the associated locally symmetric space. So there's sort of this degeneracy you can just observe that sometimes you'll see the forms in different degrees. And the conjectures sort of connect this, this just observation that's purely sort of on the automorphic side to higher algebraic cycles. So something close to sort of subvarieties of varieties, and the higher, I'll explain what that means in a little bit. And so these abstractly can be thought of as some motivic cohomology groups, if you like. And that's why they're called the motivic action conjectures. They say sort of that these motivic cohomology groups sort of act on the contributions to cohomology and explain all the contributions. Okay, so this is some very abstract, high-level overview. But actually today I'm just going to focus on 2 examples. So the goal for today is just to discuss 2 examples. And the first of those examples is Bianchi modular forms. Bianchi modular forms. So these are automorphic forms where I take the group to be GL2 over K, where K is an imaginary quadratic field. So it looks like Q squared of minus D, or a positive number D. And this is going to be really an exposition of the work of Prasanna and Venkatesh, so one of these original papers. And I should say that their paper is much more general, so it really works for any reductive group and tempered representations on any reductive group. But I just want to focus on this particular example because Bianchi modular forms of weight 2 should correspond at least to elliptic curves. So, but not elliptic curves over Q, but over this quadratic field. So So there's some sort of geometric interest you can have. So this is this sort of motive that you have in mind. So this geometric object is an elliptic curve. Okay, so I explain this example, and then I'll explain this joint work with Kartik on Siegel modular forms. So here the group is GSP4 over Q, and there is this paramodularity conjecture that predicts that, well, paramodular Siegel modular forms correspond to abelian surfaces. So this was, I guess, exactly what one should say here was figured out by Brummer and Kramer, and I want to defer the details to maybe that paper. But let me just broadly say that the motive you should have in mind here is an abelian surface, because I will be looking at Siegel modular forms of weight 2 once again. Okay, so I should maybe say Bianchi modular forms of weight 2 and Siegel modular forms of weight 2. Okay, all right. And I'll just mention in passing that one could also consider Hilbert modular forms, and this is what I did in my thesis, but I'm gonna sort of focus on these more geometric cases today. Okay, so let me now start with example 1, which is Bianchi modular forms. Oh yeah, and I should say, feel free to stop me at any point if either something is unclear or like I scrolled down too fast or something like that. It's a little bit difficult to keep track of what you can see. It's easier when you have many boards in front of you, rather than just this one screen. Okay, so we're considering GL2 over K, and K is this imaginary quadratic field. And we consider, okay, so modular forms are functions on the upper half plane that satisfy some transformation properties. Bianchi modular forms will live on something with bigger dimension, namely the hyperbolic space of the hyperbolic free space. And so a model of that could be just taken as a copy of the complex numbers and the positive real numbers. Let's call these variables here Z and T. And Z is going to be X plus IY, just for later. And okay, so this is the hyperbolic, a model of the hyperbolic free space. And I guess I should tell you what the hyperbolic metric is. So ds squared is something like dx squared plus dy squared plus dt squared divided by t squared. Okay. All right. So this is what this object is, and the interesting thing is that it admits an action of GL2C. So this is similar to the way the upper half plane admits an action of well, GL2R, or maybe the positive matrices there. Okay, and so within here we can see sort of the integral matrices associated to K. So GL2OK will sit via some fixed embedding inside of GL2C. And you can look at some congruent subgroup gamma, and then define what Bianchi modular forms is in forms should be in terms of this action. So let me now say what a Bianchi modular form of weight 2 is. Okay, so it's going to be a function on the upper half plane, on the, sorry, not the upper half plane, but the upper half space, and it's going to land in C3, so it'll sort of be vector valued. So in other words, I can write F, F1, F2, F3, where these are free functions. Okay, and it satisfies a transformation property, under gamma. Okay, I'm just going to write, it's a bit cheeky, but I'm just going to write that there is a slash action which under which f is invariant, and then I'll tell you how you could figure out what the slash action is. So you should have some sort of slashing similar to modular forms. And instead of writing down exactly what it is, I'll tell you how you can figure it out. So equivalently, the way the definition is set up is that if I write the following differential form, so omega f1 is going to be the first function, and then I'm going to look at dz divided by t, minus the second function and dt divided by t, plus the third function dz bar divided by t. So this is some differential form, maybe on H3. And the way the transformation property is set up is that it actually descends to H1, H3 mod gamma, so to the quotient by gamma. So in other words, this class itself is gamma invariant. And that means that f should transform in some specific way. Okay, so equivalently 1, or you could look at another class, which I'm going to label by 2 because it will be a sort of a 2 form. So I'm going to similarly do f1, f2, and f3 and put some decorations on them. So I'll do this one divided by t squared, and then plus the third one, dt wedge dz bar over t squared. Should be a class in H2, H3 mod gamma C. Okay, so let me box this off. This is the definition of a Bianchi modular form. And I should say maybe parenthetically that actually 1 is equivalent to 2, is equivalent to the transformation property. So you could assume either of these, and then the rest will follow. Okay, so you immediately observe this sort of phenomenon that there is a sort of 2 different classes that you can write down associated to the Bianchi modular form. I can put these differential forms on it, or those differential forms, and somehow I got 2 different classes this way. Okay, now when I started the talk, I maybe started with the Langlands program. And so we should maybe figure out how these Bianchi modular forms fit within the Langlands program. Ooh, there's something in the, yeah, so there's a question also in the chat whether the function needs to satisfy a differential equation so that differential forms are closed. And yes, the answer is yes. Maybe I should say harmonic or something to this effect. Yeah, thanks for the question. I was being a bit, yeah, so I guess normally the condition should be, for a modular form, you should assume it's holomorphic, and here I should assume some version of that. Thanks. Okay, so we wanted to make things fit within the Langlands program, but we can immediately note the following thing that gets us into a little bit of trouble, that this quotient, so I just said it, so H3 has real dimension 3, so this is a real threefold. And so it cannot possibly have an algebraic structure. I mean, if it was a variety over Q and you looked at its C points, that would be even dimensional. So it cannot be the C points of an algebraic variety. Okay, but nonetheless, there is a way to associate Galois representations to these things. So if you look at Bianchi modular forms of weight 2, there's a way to associate a representation of GK, where G is, so this is the absolute Galois group of K landing in QL. Okay, maybe I'm assuming some sort of integrality so that I don't have to take QL bar here. And so this association was due to Harris, Sudri, and Taylor originally. And the way it goes actually is quite interesting. You sort of look at the Bianchi modular forms, which live on this hyperbolic free space or a quotient of it, and you transfer them to a Shimura variety. the Siegel modular variety. And then you sort of construct the Galois representation there, and then say it's the correct Galois representation. So I'm just going to say that the way they do it is actually by a transfer to GSP4. Okay, and now I told you that, well, first thing, you can actually just observe that if you take an elliptic curve over K, I guess, then it will certainly give you one of these representations by looking at the Tate module. So you certainly have a map this way, and maybe recent work of Kariani and Newton will tell you that most of these E over K are modular. Okay, so they have some various assumptions, but for a large class of such elliptic curves, they can conclude that they actually come from a Bianchi modular form. Okay, so we're just going to assume this. So we're going to sort of assume that our F here sort of corresponds to some E over K, which is an elliptic curve. Okay. All right, and our goal now is to, so I told you these differential, this sort of differential forms associated to F, and I wrote the singular cohomology with C coefficients up there, because these classes actually will not be rational. And so the next goal I want to try to sort of set myself is to understand the rationality of these classes, omega f1 and omega f2. And I'm going to say loosely sort of in terms of E. So I would like to understand sort of how proper, like how the elliptic curve knows about the rationality properties of omega f1 and omega f2. Okay, so let's just draw a little diagram. So we have this H3 mod gamma with C coefficients, right? And over here we had the class omega f1. Sorry, I'm not giving myself enough space, omega f1. Okay, and then somehow there is this H2, H3 mod gamma C, and here we have the class omega f2. And we would like to know what, maybe over here there is a rational structure, which is given by the rational singular cohomology. And it turns out, and then also over here, let me just write it down. So H3 gamma Q. And the lucky thing actually is that if you look at the action of the Hecke algebra and you sort of look at just the part of the cohomology where the Hecke algebra acts with these Fourier coefficients, all these spaces will be one-dimensional. So you'll actually know that some multiple, so over here, there'll actually be some multiple of omega f1. If I divide it by the right complex number, I'm gonna get a rational class just because these are one-dimensional vector spaces. So actually, already abstractly, there should be some complex numbers, and I'm trying to interpret them. Okay, so the first rationality of this H1 class is a conjecture due to Cremona and Whitley. That sort of the period that you get out of this form should be the following thing. You'll take a narrow differential on the elliptic curve, and you'll sort of wedge it with itself and integrate that over the elliptic curve. So here, I guess I chose an embedding of K into C so that I can talk about the C points. And omega was a narrow differential. So this is some sort of volume associated to the elliptic curve, maybe a Falting's height, as it's sometimes called. Okay, so okay, and then over here is where this conjecture of Prasanna and Venkatesh comes in. Is about sort of the rationality of this class in some sense, or it can be. It can be formulated as sort of which multiple of this should be rational. Okay, And for that, I'll tell you one extra thing. So I'm going to draw a picture of the elliptic curve and the product of the elliptic curve with itself. So this is just a picture of E times E, where I'm thinking of the two axes as E. And within here, I'm going to give myself a collection, C1, C2, C3, of some irreducible curves. And on each of these curves, I'm going to choose a rational function. Sorry, a meromorphic function. Well, yeah, a rational function. That's what I want to say. So map to P1 on each of the curves. Okay, so this data is going to define this higher algebraic cycle that I mentioned in my introduction. But so what I want actually is, okay, so the following data of maybe some collection of Ci phi I, where first of all, Ci is in E times E, and it's some irreducible curve. Phi I is a function on Ci. And I want sort of the sum of the divisors of those functions to cancel out. So I want the pole. So let's say if the first function had a pole here, I would want to cancel it with a 0 of the second function over there, and so on. And what you have to then divide by in order to get rationality is something exactly in terms of these collections. So I should say maybe that the conjecture is that there exists some alpha Ci phi I with the following property. What I want to divide by here is sum of the integrals of those functions. So I look at all the curves and I integrate the log of that phi I against that curve. And of course, that doesn't in itself make sense. You need some 1-1 form. So I'm going to write delta, where I'm sort of running out of space. Let me write it here. So delta is an explicit 1-1 class on E times E. And so I'll write it down for you. So the way you could get one of these is take sort of omega sigma wedge omega sigma bar. So there's another embedding of K into C, which is the complex conjugate. And you could look at this wedge of this with the omega sigma bar plus omega sigma bar wedge omega sigma bar. So sort of you take the two possible sort of neuron differentials and you wedge them in this way. And this gives you a 1-1 form that you want to integrate. Okay. I think this is the explicit class that I want. Okay, so here's one way you could think about this whole story. So I gave you some like explicit ways in terms of the elliptic curve to predict the rationality of omega f1 and omega f2. And maybe one perspective taken in this work of Prasanna and Venkatesh is that there's this very natural map going from H1 to H2, which is to just send the first form that you get to the second form that you get. But this map is not rational. I mean, neither of the things are rational, and you have to rescale them in different ways. And so, okay, this is not going to be a commutative diagram if I do it like that. But over here, you more have a map that sends this class to that class. And so they think of this map, which I wrote down very explicitly, as an action. So this is like an action of this alpha. Remember this alpha, which is really a motivic cohomology class written very explicitly.
Sorry, Alex, there's a question on the chat. I can read it out loud if you want. It's from Aaron Pollack. He asks, in these rationality conjectures, how is the Bianchi modular form normalized via the Fourier coefficients?
Yes, perfect question. Yeah, it's something I should have said, which is that the answer to this question is yes. Thanks, Aaron, again for the question. Yeah, please keep them coming. Yeah, so here F is both sort of omega F1 and omega F2 are Whittaker normalized. Normalized in some specific way. Okay, so, all right. Okay, so I'll just state this conjecture explicitly in more generality. So I mentioned that this is quite general. Let me state it like this, just so you get a flavor of what this general conjecture looks like. So gamma will be any arithmetic sort of group. So this is like sitting inside of the Q points of some reductive group. And pi is going to be a tempered representation. So tempered cohomological representation of GA, automorphic representation of GA. And the conjecture will sort of say that there'll be some motivic cohomology group. So I'm going to write H1MZ, so that sort of integral motivic cohomology group of the adjoint motive of the modular form or the automorphic representation should act on, okay, I've not given myself enough space. Okay, I wonder, maybe, let me just move this to the side and put this here. Okay, so pi is this automorphic representation. So if I look at this adjoint motivic cohomology, it should act on sort of all the contributions to cohomology of pi. And I've written things here in terms of group cohomology as opposed to the cohomology of this quotient, just for simplicity of notation so that I don't have to introduce this locally symmetric space. But this is what the general conjecture looks like. And actually they don't say, so they say sort of, okay, so one way like to phrase this is maybe that there exists some action like this, but their conjecture is a bit more precise. So what they actually say is that they define an explicit action, which is of this form on cohomology of the Deligne cohomology group. And then you have this regulator coming from motivic cohomology. And that action should be, that action of the Deligne cohomology, the resulting action of motivic cohomology should be rational or something. Okay, so what I wrote about here is sort of an explication of that. All right, so I hope I didn't make it too confusing. But okay, so there's an explicit statement and then there's some very abstract abstract phrasing of this that applies to many situations. Okay, so the actual goal of my talk is now to explain how to make this work for Siegel modular forms. So G is GSP4 now, GSP4Q. And in this case, okay, so I should first note that the above conjecture is sort of only interesting. So this should be like a derived action. So it should be shifting degrees. And it's only interesting when you have multiple contributions to cohomology, like I said. But actually, Siegel modular forms will never contribute to multiple cohomological degrees. There won't be this spread in cohomology of tempered forms. So there's this invariant called the defect, and it would be 0 in this case. So the above conjecture is kind of vacuous in this case. And instead, we have to consider something slightly different. Let me first tell you what Siegel modular forms are. So previously, we had this hyperbolic free space as the analog of the upper half plane. Now we'll have like another higher dimensional version of the upper half plane. This time it will be given by 2x2 complex matrices. So this is just going to be 2x2. But I'm actually going to make them symmetric. So symmetric 2x2 complex matrices. And normally in the upper half plane, we assume that the imaginary part of Z is positive. So the correct analog here is to assume that this matrix is positive definite. And now this is called the Siegel upper half space. Okay. So it's complex dimension free, if you're keeping track. Okay. and this will have an action of GSP4R. It's actually, okay, one can write it down pretty nicely. So if you take some matrix, some block matrix A, B, C, D, you can sort of send tau to something very similar as on the upper half plane, but now you're dealing with matrices. So you put an inverse instead of actually dividing numbers by each other. Okay, and what I'll define for you right now is a holomorphic Siegel modular form of weight 2, which will look similar to a modular form. So holomorphic Siegel modular form of weight 2 and level gamma. And this is some subgroup maybe of GSP4R. Okay. It's going to be a function on the upper half plane, on the Siegel upper half space, which is holomorphic. This time it's just valued in C. And there is a slashing action, a weight 2 slashing action for all gamma in gamma. And previously I sort of didn't say exactly what it is here. Maybe it's a little bit easier. And so I'll write it down. So if I slash the form and I evaluated the tau, it should be the same as in modular forms. You would have CZ plus D to the -2 coming out. Here it's the determinant of this matrix C tau plus D, the -2 times F of gammas. So this is the slashing action. Okay. So this is this definition. Okay. So in this case, we're in luck in some sense. So in this case, if I look at this quotient of the, let's say some compactified quotient of this upper half space, it is actually the C points of a variety over Q. So there's a Siegel modular threefold, really defined over Q in this case. So real dimension 6. So it's a bit misleading with the threefold and the threefold, but this is really an algebraic thing over Q, whose C points are this quotient. So you could imagine maybe that F defines now these sort of differential forms on this upper half space, but it turns out that this weight 2 is sort of too low for that. So however, F is not what is called cohomological. So in other words, if I look at like cohomology in any degree, I guess, of the C points of this Siegel modular variety, and I look at the Hecke eigensystem associated to F, this will never appear in cohomology, not even if you take a local system. So also with local systems. It's more a remark for experts maybe. The point is it's not cohomological, but once again, it seems possible to associate Galois representations to these objects. So if I look at Siegel modular forms of weight 2, by the way, so a good analogy to have in mind is that these sort of behave like modular forms of weight 1. So they're too low to be seen directly in cohomology. Okay, and these give you still Galois representations, and these Galois representations are valued in GSP4QL. The dual group can be identified back with GSP4. And so this construction, I think, was due to Taylor, and it's sort of the analogous thing to the lean Serre. So it sort of uses congruences, using congruences with higher weight forms that are cohomological. Okay, and once again, the geometric objects here should be abelian surfaces over Q, which give the right Galois representations, because you have the Tate module, and then that fixes the a Weil pairing. So indeed, there's this symplectic pairing. And I guess here I can say that there's this work of Boxer, Caligari, G, and Piloni, which gives maybe, which sort of says that these A over Q are potentially modular. And I heard maybe that there's some hope of upgrading this again under some restrictive hypothesis, or more or less restrictive hypothesis, to actual modularity. Let's say, for now, we know it's potentially modular. But there's another subtlety that will be important. So let me just say subtlety. There's actually a packet. So maybe this is like an A packet or an L packet. Okay, so there's some packet which consists of sort of a holomorphic representation and a generic representation, which both map to sort of the same Galois representation, one Galois representation. So, and you have this modular form that I wrote above, so this holomorphic Siegel modular form, it's actually an element of this first representation. So it belongs here. This is a holomorphic Siegel modular form. But the strange thing is that there is another modular form, which I'll write FW, which belongs to the representation, which is a generic discrete series. And I'll call this a generic Siegel modular form. And in this case, the W is because, so generic means that the representation has a Whittaker model, and I want to sort of normalize it using the Whittaker model. So in some explicit way, it's Whittaker normalized. On the other hand, the holomorphic one is not generic, so you can't actually use the Whittaker normalization. So there's some sort of, the representation theory of GSP4 is a little bit harder than the representation theory of GL2 above. Okay, but okay, so let's assume in any case, once again, that our sort of, we have this abelian surface. So we have maybe the set of two different representations, pi hol and pi gen, which corresponds altogether to this A, which is an abelian surface over Q. All right. Okay, so now I would like to ask this question, because, right, so previously we had a Bianchi modular form, we saw it in cohomology, and we sort of said that maybe the geometry of this elliptic curve knew something about the rationality of those contributions, but I just explained to you that you can't even find these forms in cohomology, right? So where can we find F and FW in cohomology? So this is the next question I have to answer. And the way the story goes, again, is maybe similar to weight one modular forms that are found. So every holomorphic modular form is a section of a certain line bundle. So let me just say this as a fact, that there is E over X, which is a certain line bundle. This is going to be sort of the line bundle of weight two Siegel modular forms. It's an automorphic line bundle. But I guess all you need to know is that there's some line bundle such that, first of all, this F will define, so the holomorphic form will just be a section of this line bundle. And I'll even assume that it's a rational section. So, okay, this is maybe like normalizing F to be rational right now. As I said, there's no good way to normalize F. So let's say F defines a rational section. And this other vector, I'm going to be able to find it in the H1 of this line bundle, in higher degree of cohomology. But now you have this sort of these coefficients. So I'm writing pi again for the sort of isotypic component associated to the Hecke action that determines this this packet here. Okay, so that's where you find this in cohomology, and maybe let me finish this by saying that these are all the contributions, and so i.e. h star of x c e pi, let's say, is 0 for star not equal to 0 and 1. And also I want to say, I guess, that these parts are actually one-dimensional. Okay, so let me state this as a fact and just move on. Okay, so we found these in cohomology, but now in the cohomology of these line bundles. But again, we have a degeneracy, right? There is a class in H0 and a class in H1. And so you can ask about the rationality of the map that sends the class in H0 to the class in H1. And so this is the conjecture in my work with Kartik. So at this point, it may hopefully seem natural. So there exists some alpha, which is a collection of, let's call them zi phi I. And okay, so this is a similar, so the picture is very similar to before. So you have now we have abelian surfaces instead of elliptic curves. So the total thing is 4-dimensional, but I'll still draw it sort of in a 2-dimensional way. And you have this z1 here and z2 and so on, and functions phi I on them. But now maybe these are irreducible free-folds in a 4-fold or something like that. Phi 1, phi 2. Sorry, this was phi 1. Okay, so you have maybe zi in a times a, which are free-folds, irreducible free-folds. You have phi I, which are sort of meromorphic functions, rational functions on them. And the sum of the divisors of phi I should be 0. So this is this higher algebraic cycle, such that okay, and then so now this is the rationality statement. So I should tell you sort of, you have this map from H0 to H1, and over the complex numbers, you can send this f to fw. And so f was already rational in this case. So there's no way to normalize f, as I said. So f, you just have to normalize it directly to be rational. But then when you send it to fw, you'll see some very similar thing coming up, at least conjecturally. So sum of the integral of over these cycles, ci of c, of the log of the absolute value of phi I, and then times delta, where now for things to make sense, delta is an explicit free class on a times a. Okay, and maybe if you choose a basis of the differentials on a, I could write down explicitly what this class is, but you can imagine it's something similar to what I wrote above for elliptic curves. Okay, so this is the conjecture. So any questions at this point? Anything in the chat I missed? I don't even know how to check, I guess. Okay, so hopefully so please warn me again if there's something in the chat, because I lost the ability to check myself. I don't know why. Okay, good. So this is the conjecture that we state in our paper. And so the first thing I should say is that, so now I should maybe convince you that it has a chance of being true. So let me first state a theorem. So I'll try to state 3 theorems. I think I'll have time for that. So this is the first theorem. And this theorem is that this conjecture is implied by Bailenson conjecture. So Bailenson's conjecture on special values of L functions implies our conjecture. And actually, it implies our conjecture only sort of up to Q ab cross. So our conjecture is a rationality statement. And right now, we only get sort of a rationality statement up to multiplication by some roots of unity, maybe, or something like this. And I'll say now, like, I'll say in a second where this comes from. And so for that, I want to give you sort of a sketch of the proof. It's a math talk, so we can do at least one sort of fake proof. I want to say, I just want to give the sketch of the proof because I guess it's not immediately clear what any of this has to do with L values. And it's not, and so I would like to show you how we can relate it to some statement about L values. So note that the whole point of the conjecture is to understand the rationality of this class FW in H1. Okay, so that's sort of the goal. Sorry, so it's not rational a priori, and then we want to understand its rationality. Okay, so here's what you can definitely think about. So we have this class over here, and you can think about pairing it using Serre duality. So let's look at Serre duality, and let's look at, okay, so it's a threefold, so Serre duality will pair H1 of H2, and okay, there'll be the sort of dual bundle tensor omega1, omega 3x, sorry, the canonical bundle here. Okay, and over here, there's sort of going to be a dual Whittaker class as well. Okay, and so on both sides, you have a rational structure. There's this rational structure, and these things are also defined rationally. So there's a rational structure over here. And of course, Serre duality is a thing that preserves the rationality. So you have a pairing between the rational structures. And you would really want to know something about this rationality over here. So here, maybe you'd like to know what multiple of it ends up being rational. And I'm sort of saying that maybe if you paired it with this guy and knew something about the pairing and also knew something about this rationality, you would be able to sort of figure out what the rationality on this side is, if that makes sense. So here, this rationality is actually sort of understood, at least well, it's understood in the following sense. So, sorry, I'll write it. I was going to write it here, but I don't think I'll have space. So what do I have to divide this class by in order to get a rational class? So this will have something to do with the L function of pi already, okay? So here, maybe I'm going to refer to work of Leffler, Piloni, Skinner, and Serbies. Although maybe these ideas go back to Michael Harris in a slightly different way. But in any case, this class in H2 is rational after you divide it by some sort of L values, tensor chi minus. Okay, so chi plus and chi minus here are even and odd Dirichlet characters. And so you can imagine, like, what I'm actually saying is that maybe there's an integral representation for this product of L values that involves this Whittaker normalized form. And so the rationality is predicted by the rationality of these L values. Okay. So first of all, there's this result that we sort of, okay, so in some sense, we understand the rationality on this side. And then we want to use the following things. So first of all, we should understand the pairing of the two classes if we're going to have a chance at using this. Unfortunately, this is like the Peterson norm of the Whittaker normalized form itself. And there's work of Chen Ichino. So Chen and Ichino gave a very explicit formula relating this to the adjoint L value. Okay, and then second of all, there's work of Rajivu and Yang, which is sort of an analytic result that actually says that there exist some characters, chi plus and chi minus, which are even and odd, such that those L values are actually non-vanishing. Okay, because I divided by them, so I better know that they're non-vanishing. And indeed, they prove that there exist some characters for which they're non-vanishing. And the reason this factor up to Q up cross comes up is that these characters could have arbitrary order, so they could sort of introduce some roots of unity in their values. And if we knew a stronger result, for example, that there exist quadratic characters, which is known for GL2, then we could remove this as well. Okay, so I'll say maybe this doesn't, I didn't really prove anything, but I'll still draw a square. So far what we did is we took this form, we want to understand its rationality. Via Serre duality, we sort of related it to understanding this rationality and the Peterson norm. And now comes something that becomes a bit difficult, but can be done, is to sort of say that Bailenson conjecture for this L value, together with sort of understanding these L values, gives you an explicit statement of the form I wrote above. So somehow there's some explicit calculations with Bailenson's conjecture that give you the expectation. Okay, so any questions about that? So maybe I should say this a bit more explicitly. So then like some explicit form of Bailenson is needed to get, like these L values have to somehow go away, and this L value has to give you some Bailenson regulator. Okay. All right, so in the last few minutes, I want to talk about some special cases and actually tie things in a second with what I talked about at the beginning. So the special cases I want to consider, first of all, an elliptic curve over F, which is a real quadratic field. Okay, and the associated restriction of scalars, which is now an abelian surface over Q. So this very restriction of scalars is sort of like taking E and the twist of E by the non-trivial Galois automorphism and descending that to Q. So this gives you an abelian surface. And at the level of automorphic forms, sort of this gives you a Hilbert modular form, or conjecturally, this should be a Hilbert modular form. And then this abelian surface corresponds to sort of the Yoshida lift of that Hilbert modular form. Okay, so then I can state theorem 2, also in this joint work, that in this case, we can just prove the conjecture. So the conjecture is true. So previously we knew maybe that it's true up to Q ab cross, and also we had to assume Bailenson's conjecture. The idea here is that we can sort of use this work of Ramakrishnan, who constructs explicit motivic cohomology classes on Hilbert modular surface, and sort of translate that to this Siegel setting. And so I should say maybe just verbally, since I'm running out of time, that of course the conjecture is right now, as stated, conditional on the fact that F corresponds to an abelian surface. So in that sense, it's a meta conjecture, the way I stated it. But there's also like just a conjecture about the Siegel modular form itself directly. And so then that doesn't depend on assuming that F corresponds to an abelian surface. And so there is some statement that's actually itself unconditional, and therefore it makes sense to say this conjecture is true without sort of also assuming some auxiliary conjectures. Okay, and then I just want to finally connect things back in the case of elliptic curves, elliptic curve over k, where k is q squared of minus d. So we already discussed this case, right? This is where you have a Bianchi modular form. Bianchi modular form. And once again, you can produce the restriction of scalars. And this will be, again, a Yoshida lift in some sense of the Bianchi modular form. And in this case, we can prove the following theorem. Okay, so so the way I'll state it is that our conjecture implies the conjecture of Prasanna and Venkatesh. So in other words, the conjecture I stated before of Prasanna and Venkatesh is implied by this conjecture I stated. But there's actually a very nice thing you can do to make it more precise. So more precisely, there's actually a commutative diagram that looks like this. First of all, you had this, okay, let's call this, okay, there's this thing. So let's call this Bianchi modular form Fk, and the Yoshida lift F. So here you have Fk, and the action of Prasanna and Venkatesh gave you sort of a map like this that preserved rational structures, or conjecturally preserved rational structures, but there was certainly a map after your tensor with C. And via these sort of lifts, you can associate classes over here. So, and then on this side, you'll have sort of our conjecture. And the assertion is that this diagram is commutative. And in fact, the whole point is that this diagram is commutative. Like that statement is independent of Bailenson conjecture once again. So it's not like assuming Bailenson's conjecture, the two are equivalent. This diagram just commutes up to Q cross or something without assuming any general conjecture. Okay, so I'll finish here. Thank you very much for listening.
Luis, I think you're muted.
Yes. Thank you very much for a beautiful talk. Now it's time for questions. So if anyone has a question, please unmute yourself and ask.
Yeah, thanks for the nice talk. I have a question about your theorem. I guess the theorem 1, when you have this valence conjecture implies your conjecture, and then here you have so just a naive question: why do you have rational structure on H2? Is it because of the you take the dual of this E and then tensor it, or why don't you have?
Oh, sorry. So yeah, so I guess I should have said, so E itself, E is defined over Q, first of all. So I should have, I don't know if it was clear when I said it back then, but E, like you have this, okay, so you have X, which is over Q, and over it you have a line bundle E, which is over Q. And then this E dual will also be defined over Q. And also this omega-3x will be defined over Q. And when you tensor them together, that will also be defined over Q. So in other words, every object here is defined over Q. So it makes sense to take sort of the coherent cohomology in this rational world. So this sheaf cohomology.
So you can already do that in H1, right?
Yeah.
Okay. And then the question is this 3 question marks on the denominator for this H. Okay, and then in order to figure it out, you have to go use their duality and.
Yep. So I don't know the rationality of this one, but the rationality of this one
other side
is a bit easier.
There's one directly factor.
Oh, sorry, I didn't quite catch that. The last thing you said.
No. I was saying that 3 question marks on the denominator on the left-hand side, there is no way to directly figure it out what it is.
Well, at least I don't see a way. Maybe somebody else would have some ideas, but like our method of proof was to relate this rationality to this rationality together with the knowledge of the Peterson norm of the form. But it's possible that somebody else would have a way to get directly at this rationality. But I should say that in general, like figuring out the rationality in these cohomology groups seems quite difficult. At least, yeah, I don't know, this question of just like what multiple of a form is rational, if you have defined a form using like a Dolbeau homology class, it seems like quite difficult to figure it out directly.
I see. Okay, and just another question about these characters, chi plus chi minus. How is this, I mean, how is it involved? It's not related to f at all, right? It's some choice.
Yeah. So there's some choice of the characters, and so yeah. So I was yeah. So what I should say is like you can take this class, and then actually what you do is you take some Eisenstein series with like a pair of Eisenstein series which are maybe associated to these characters, just Eisenstein series on GL2, and you restrict this form to the embedded product of modular curves, and then you integrate against those things. So somehow, and then because you know something about the rationality of the Eisenstein series, you recover this statement. And okay, and this is where I'm being like a bit sloppy, because maybe what I should say is that here I'm tensoring with Q adjoins sort of the values of these characters. And so that's why you only get the statement up to Q app cross, because here you can only get the rationality up to like these unknown characters whose values will play a role.
Okay.
But yeah, good question, thanks.
And so I don't know, can you introduce a Galois action on these directly characters so that you can get rid of these factors in Q app?
Yes, so
reduce it to Q cross?
Yeah, so the issue, I guess, is yeah, somehow I don't know if that's because the class is what it is, as you said, right? It has nothing to do with the characters. Right. And it's more like I choose some other characters and sort of some Eisenstein series associated to them and integrate. That auxiliary data is what increases the coefficient field. But the auxiliary data depends on this analytic result that says that some L value is non-vanishing. So the Galois action, like, as you say, there could be a Galois action that maybe like, it's not clear that things will not be vanishing. Like this result is really analytic. It just says that there exist actually infinitely many such characters, but it doesn't say like which ones, or you don't have control right now over their order, which is the issue.
I see. Okay, so this pi is over Q.
Pi, the automorphic representation.
Yeah.
Yeah, it has, yeah. Like pi f is defined over Q or something, yeah.
Okay, so I don't know if the Galois action that you put on the character, if you can also bring it into the tensor with pi, and then maybe there's some relation between special values for automorphic representation and this twist by some Galois, and then I don't know, that could be used to give you vanishing if you replace chi by some Galois twist.
Yeah, it's possible. I guess I would have to think about it. Yeah, you're right that the Galois action should fix pi itself because pi is rational. So can you act on the whole thing and get something out of it? Yeah, it's possible. I'll have to think about it. Thanks for the suggestion.
Okay, yeah. Thanks. That's all my questions.
Thank you.
Any more questions?
I just wanted to make one more comment actually about this kind of result and also this kind of result that I use in this proof, because I forgot to say it during the talk, but both of these results are known for GSP4 and not for any higher GSP2n, or, well, this result could be stated for GLN, and really 4 is the boundary of what the analytic methods give you. So, yeah, our paper is really for GSP4 and not higher GSP2n's, and things seem to get much more complicated. And even results like this are just not known beyond this case. Yeah.
So I wanted to ask a question about, so at the beginning when you first started Venkatesh's conjecture, you had some motivic cohomology group, quite abstract. Yeah, and then at some point you had these higher algebraic cycles. So in practice, can you, when you derive concrete instances of these conjectures, like the one that you have told us about, can you always basically realize it on cycles made on products of abelian varieties with themselves and so on?
Yeah, so unfortunately it depends, right? So maybe I stated this. So this is the real motivic cohomology group that you want. And so the question is the, like for some pi that you start with, is the motive M of pi, you know, do we know where we can find it? It's the first question. I guess the conjecture for a Siegel modular form of weight 2 is like M of pi is maybe related to H1 of the abelian surface or something like that. And so this is this conjecture. And then actually we want to look at the adjoint motive. And in this case, for example, that I studied, the adjoint is like a twist of the symmetric square. And so, okay, up to a twist. But the point is that then you can maybe realize this in H1A, tensor H1A. And in this case, this will sort of sit inside of, I don't know, H2 of the product. And so this is what I'm using to write down something within the product. I'm sort of realizing that, okay, if the motive itself is somehow associated with A, and the adjoint motive is related to the symmetric square, and that can be realized within the tensor, then I'll get something in the product. And in general, you know, like the conjecture of Prasanna and Venkatesh, they just assume that there exists an adjoint motive. We don't even know, I guess, what the motive itself would look like in general. But if you have some case in mind where you sort of expect to see the motive in some specific place, then within the product of those things, maybe if the adjoint is related to the symmetric square. Yeah, so it also depends on what your adjoint representation looks like. Yeah.
I see. And so in this example that you're showing right now, I think you mentioned this towards the end of the talk, that you have written this as an integral over curves in E, but somehow you can replace this as an integral over the modular, over some sort of modular curve or something like this. Is that right?
Yeah. So right. Let me think what I want to say. Right. So I said that there is some version, I guess, of this conjecture, which doesn't actually require you to go to an abelian surface, I guess, but you still have to like go to the motive associated to F. So somehow, like the way the conjecture would go is maybe you assume you have some F and you have the motive of F, and then you would look at like motivic cohomology of the like H3M of the symmetric square of the motive Q2 is the right thing to look at. Okay, so the motive itself, like we don't know how to get it, but in this, so what I'm saying, what I was trying to get at is that in this case of the elliptic curve over here, somehow it turns out that the symmetric square motive is also sort of associated to the assi motive of F times the adjoint motive, the assi motive of the Hilbert modular form and the adjoint motive of the Hilbert modular form. So somehow those motives are easier to construct than the original thing. And you could take that as an avatar for your symmetric square motive. And then you get some unconditional result. Yeah, so it's a bit tricky. Like it doesn't depend on the abelian. Like you need to assume that there's a motive to even state the conjecture.
Right. Okay.
Yeah.
Okay. Thank you. Are there any other questions for the speaker? Okay. Well, in that case, let's thank the speaker again. And I think we can now stop recording.